I will discuss the doubts related to fluid. Page 8. Question 10A2. Okay. In the question 10A2, the ball is spinning in the direction as shown in the diagram. Suggests where there is a larger region of a turbulent flow on top of the ball. Suggests why there is a larger region of a turbulent flow on the top of the ball than the bottom. So what is the reason? When you check, look, this is the surface of the ball. So the movement of the surface of the ball, as it is, this is the direction in which the ball is spinning. So the movement of the surface of the ball and the motion of the fluid is opposite. So that is why here it will experience the maximum force, and as it will experience the maximum force, there will be greater turbulent flow, because the turbulent flow depending on the movement of the object and direction in which the surface or the movement of an object. So because it is moving opposite to the direction of the fluid, a fluid is moving towards right, the surface at point A is in opposite direction, that's why it will experience maximum force. So greater turbulent flow at the top as compared to that in a bottom, because you can see the surface, the movement direction of the surface and the direction of the fluid is same, so it will not resist the motion too much. That's why less turbulent flow or smaller force will be there from the bottom. So there is small upward force, greater downward force. As a result, this ball will come down on or land on the table. The diagram shows the air is deflected upward after passing the ball. Explain why this means. There must be a downward component of a force on the ball in addition to the weight. So what is the reason why there is a downward force? You have to use a Newton concept of a Newton law. Action and reaction forces are equal but opposite in direction. So when we compare these air particles, fluid, so what happened if there is a force on the ball which is downward? So there should be a force. According to Newton's third law, action and reaction forces are equal and opposite in direction. So if there is a downward force on the ball, the Newton third or pair force will be upward force on the air molecule. That is why the fluid is moving upward or air is moving upward. Is it clear? So the air is applying a downward force on the ball. So this is a force by air on the ball. And this is a force by ball on air. That is why if air is forcing the ball to come down, the ball will apply a force in opposite direction. So that will force the fluid or the air to move upward. That is why when the ball is passing, when this ball is passing, you will see a fluid direction changes a bit. Is it clear? Is it clear to everyone? Page 10, question 13. In an experiment, a small metal ball is dropped into a cylinder of oil. The time taken for the ball to fall to the bottom of a cylinder is recorded. The experiment is repeated. Which change in the ball result in the greatest decrease in time to reach the bottom. So basically, if we increase the downward force on the ball, two things are there. We want to decrease the time. We want it to take a short time to come down. So if we want to reduce the time, we want to increase the speed of this ball. So how the weight is a downward force which is acting, and the up thrust is acting upward. The up thrust is acting upward, and the viscous drag also, it is acting upward. So we want to increase its acceleration or increase its change in speed or velocity. So what we should do, we should increase the weight. And how we can increase the weight? By increasing a mass. So we will use a greater mass. So either C will be answer or D. Then we want to decrease this viscous drag force on a spherical object, that is equals to 6 pi eta r and v. So 6 pi eta r v, if I reduce the diameter, the viscous drag will also decrease. So I will decrease the upward force and I increase the downward force. So it will move at a higher speed or greater acceleration. That is why C is the right answer for this. Question 15 and 16b2. In question 15, that investigation is carried out on a drag force, the force which opposes the motion, that is called a drag force or viscous drag. On swimmers, the swimmer push off from the side of the pool with the same arms, with his arm straight ahead of him, and his velocity is measured as he glide, like without stoking, he's moving, just gliding through the water. This is repeated with the swimmer arm at its side. So you can see two speeds are there. One is when the arms are stretched straight ahead, and another one is arms are at his sides. When arms are at his side, he has a greater change in velocity or greater decrease in velocity as compared to when arms are stretched straight ahead. So use the graph, describe and explain the motion of the swimmer performing glide 1 and glide 2. So you have to use the graph and the values are there. When they say use the graph and values are written on the graph, so you can work out what quantity you can measure. Because it is a curve, or for this part it is a straight line, so you can work out the acceleration. So for both, how we explain this, for both swimmers, both cases, the velocity is decreasing. That is one thing. But decrease in velocity for glider 1 is smaller than decrease in velocity for glider 2. And what is the reason for that? The glider 2 is having a large area, so it will experience greater drag force, the force which is opposing the motion. Or you can also compare their shapes, that for glider 1 it is more streamlined, so when the fluid will flow, it will flow around him. But for glider 2, the fluid, because more surface area is exposed, not a streamlined shape, so he will experience greater turbulent flow as compared to glider 1. Is it clear? Question 15. You have the viscous drag. If you see the formula, viscous drag is equals to 6 pi eta r and v. So this r is actually referring to the size. Greater the size, so viscous drag or drag force depends on the size as well. and as well as the shape. Like example, when you compare a shape of airplane with the shape of the car, so this streamline shape which reduce the turbulent means make a flow laminar. But here, if it is a turbulent flow, then what will happen? It will experience greater force. Yes, the relation is there. You can see the surface. The surface which is exposed to the fluid directly. In question 16, an oil drop is traveling at a terminal velocity. The oil drop take 11.9 seconds to fall a distance. Show that the terminal velocity means constant velocity. So you have the formula speed is equals to distance divided by time. So distance is there, it's in millimeters. So 10.2 into 10 to the power minus 3 divided by time interval, which is 11.9. So you will show that the speed, the terminal velocity is approximately 1 exponent minus 3. It is very difficult to measure the radius of such an oil drop directly. Suggest why? Because oil drops are not a rigid oil, like you don't have a metal sphere, it's an oil drop. So oil drops are not having a rigid structure. Their shape changes. If the sideways force is more, so then it will become elliptical. So why it is difficult? You cannot measure the size, the or the radius of the oil drop. They are very small, and the second thing is they are not a rigid structure, so they can deform. You cannot place between the two surfaces. Assuming that the upthrust is negligible, show that the radius of oil drop is about 3 micrometer. Density is given and viscosity of the air. One 1.82 exponent minus 5 is there, the exponent. Minus 5. You already worked out the velocity in the previous part. As it is falling with a terminal velocity, for a small object, the upthrust can be neglected here. So we can say weight is equals to viscous drag or no resultant force if negligible upthrust is there. Otherwise, if it is falling, weight is acting down, upthrust acting up, viscous drag is also acting up, or drag force. So if it is moving or falling with a constant speed or constant velocity, there is no resultant force. So weight plus drag force plus upthrust is equal, or weight is equals to drag force plus upthrust. But upthrust is negligible, so you can consider that is 0. So weight is equals to drag force. How to find weight? Weight is mass into gravity. And how to find mass? It is density to volume into gravity. And how to find volume? Because we consider it's a spherical object. Radius is already given in the previous 4 by 3 pi r. Radius we have to find, sorry, not given. So we will work out its volume. And what about the viscous drag or drag force? That is equals to 6 pi eta, R, and V. So we have viscosity is there, density is there, gravity is there. So first we will work out like 6 pi eta, R, and V. So first we will work out its volume. So volume will be equal to 6 pi eta RV divided by density into gravity. And after working out the volume, after knowing the volume, volume is equals to 4 by 3 pi R cube. So you can find the radius. Page 14, question 6, part B. That was the part B. Then page 16D. A student tried to model a Millikan method to find the radius of an oil drop. The student dropped a ball bearing and recorded a time it took to pass between the two light gates and knowing the distance. Explain why this is not a good, because what happened when he's using a ball bearing, when oil drop is there, oil drop, because it's small weight, so it can easily balance with the upthrust or the viscous drag, so it can move with the terminal velocity. But when we are using a ball bearing, first thing, it may not reach a terminal velocity because of its weight, does not balances with the upward force. Because what he is doing, the student is dropping student drop a ball bearing, so he's just dropped the ball bearing and recorded a time it will take to fall, but he did not drop this ball bearing in a oil or a fluid. So how this one cannot matches with the oil drop method, Millikan oil drop method, because this oil drop is having a very small weight, so it can easily balance with the upward force, which is upthrust and viscous drag. But weight of the ball bearing is more, so it can not easily matches with the upward force, which is viscous drag and upthrust. That is one thing. There will be, so it will have, this will have acceleration, but this will not have acceleration, or acceleration will be zero because no resultant force is there. And when the ball bearing is moving, the condition when we apply a Stokes law, that the fluid flow around the object should be a laminar. But what happened when a ball bearing speed increases, the fluid flow around the object become turbulent. Like when you're driving a car at say 30 kilometer per hour, you don't feel too much air. But as you're driving at 120 kilometer per hour, because air molecule, the speed of the object increase, so fluid particles continuously colliding, so viscous drag or drag force will also increase. And as the drag force increase, it means the flow of the fluid become turbulent. Is it clear? Then page 25. Question 28, A3 and C. A3 and C. Explain why the upthrust acting on a raindrop is often considered to be negligible. Now, what factors the upthrust depend on? Upthrust depends on the density of the fluid. It depends on the volume of object and it depends on gravity. So these are the factors on which upthrust depends on. So why we can consider the upthrust is negligible? So as you can see, the formula to calculate upthrust is equals to density of a fluid, volume of object and gravity. Already raindrops are small in size, but density of the fluid, it is moving around, the fluid is the air. So what is the density of the air? The density of air is negligible, means small value. So this is, volume is already small and density of the fluid is also small. So two small values, when they are multiplied, the product will also become very small. That is why the upthrust can be neglected. Is it clear? Not density of displaced air, density of the fluid. The upthrust on the object, the upthrust force depends on the density of the fluid through which the object is moving, volume of the object, and the gravity. Means as a raindrop it is falling, it is the fluid which is around this is air. So density of the air is negligible, means small value. Same thing, volume of this raindrop is very small. So when we multiply, the product will come out very small. So it can be neglected. The shape of the raindrop depends on its velocity. Once at terminal velocity, the raindrop is flat at the bottom due to the laminar flow around it and remain curved at the top due to turbulent flow. Add to a diagram to show the airflow around the falling raindrop. So if raindrop is falling, if its motion is downward, the fluid flow will be upward. So at the bottom, it is a laminar flow, but around it, it should be a turbulent flow. So how we draw this? The bottom, when if the fluid is moving, that is laminar flow. But when the fluid move around this raindrop, the flow become turbulent. So you can draw more lines. I just only drew two. Direction is also important when you draw a direction of the fluid flow. It is to oppose the direction of the motion of an object. Is it clear? Because they mention in the figure, once at a terminal velocity, the raindrop at the bottom is flat at the bottom due to laminar flow. So this is the bottom. So at bottom, we should have a laminar flow. The streamlines should not cancel out each other or cut each other or cross each other, but it become turbulent and remain curved at the top due to turbulent flow. So at the top, you will make a turbulent flow. Page 28. Question number 29B. Yeah, this is question 29B. Describe how the results obtained and graphical method used to determine the value of the viscosity of glycerol. So how we can work out the value of the viscosity of the glycerol? for this, first what we have to do, we have to use the formula which is given to work out like what graph we will plot, so that we can plot a graph and work out the gradient, and using a gradient we can find the viscosity. So as you see the first part in the beginning of the question, they provide this equation. So how I can use this equation to know what will be the result or what will be the gradient of the graph? So if I simplify this equation, 4 pi and r cube and g are constant and 3 is also constant. So 4 pi r cube, 3 and g is constant. Then it will be density of the ball minus density of the glycerol equal to 6 pi eta r v. Now we cancel out this. Pi will cancel with pi. 2 multiplied by 3 and 2 multiplied by 2. And this one r will cancel with r cube, so we are left with square. So when we solve this equation, 3 multiplied by 3, so it will be 2 by 3, 2 by this 2 is there, and 3 multiplied by 3 is 9. The difference in the densities multiplied by g, r square is there because r cube is cancelled, so r square, and that is equals to, this side we are left with viscosity and v, or this 9 eta is multiplied, other side it will divide, so viscosity and v. If I rearrange the equation, only move the left hand side to right hand side, so I can say v, the velocity, is equals to 2 difference in the density g r square by 9 eta. Now what we will do, we will compare with a, basically when you want to plot a graph, you can plot a graph for the quantity which can be varied. So the quantities which you can vary, density cannot be changed, gravity cannot be, you cannot change, gravity changes with altitude, but you are not the one who can change the gravity. Same thing, the viscosity at certain temperature, the viscosity is also constant. So the only things which we can change is the radius, and when we change the radius, the velocity will also, or speed at the terminal speed will also change. So these are the two things we can plot a graph. So if I compare this with the equation of a straight line, y is equals to mx. So on y-axis, if I plot velocity, on x-axis, if I plot r square, so velocity on y-axis and radius square on x-axis, what will be our gradient? So our gradient will be equal to 2 by 9 difference in the density of the ball bearing and the glycerol, g divided by eta. So using this, so what we'll do, first you will work out this equation, then you will mention y is equals to mx. When we compare with the equation of straight line, so we'll get a straight line which is passing through the origin, and we will find the gradient of this straight line by using a formula y2 minus y1 over x2 minus x1, and the gradient of this straight line represent so the gradient of this straight line is representing the whole factor, and if we need the density, so using this whole factor we can find the density of the glycerol. Is it clear discussion how to work out the density of the glycerol, sorry, viscosity of the glycerol? So same thing, we'll have the constant, and using those constant, because after getting a gradient, so we have gradient, the densities are given, gravity is constant, so we can work out the viscosity. Is it clear, this part? Then page 29, question number 31A2. 31A2. It is observed that the large bubble reached the top of the column of a liquid in less time than the smaller bubble. By considering the forces acting on the bubble as it rises, explain this observation. Why the large bubbles are able to rise more quickly as compared to small bubbles. So basically, why they are rising? Because there is an upward force, that is upthrust, and downward force is a weight. So upthrust depends on the density of the fluid. That is same for both bubbles. For large bubble or a small bubble, the density of fluid around them is same. Second thing is volume of object and gravity. So when you check, the size is changing. So upthrust is equals to volume of object and gravity, and it is a spherical object, so 4 by 3 pi r cube. Density, gravity. So what it shows, when we change the size, upthrust is proportional to r cube. Like if I double the size, it will increase by factor 8, the upthrust. But when we increase the size, the weight will also increase, or the drag force will also increase. But when we compare the drag force or viscous drag, so how the drag force or a viscous drag is related? Drag force, that is 6 pi eta rv. So the force which is opposing, like the upthrust is acting up and the viscous drag is acting down, it's trying to oppose. So it shows that the viscous drag or drag force is directly proportional to radius, or it can be radius square when you work out the formula, completely changing, but it is proportional to radius. So it means when the radius is double, the viscous drag will be doubled. So what it shows, like if I use the numbers, the values, example, this was say 2 meter cube, example this is, and this one is 4 meter cube. If the 2 meter cube was experiencing the upthrust of 10 Newton and the drag force or the viscous drag was 5 Newton. But what happened when we double the size? If I double the size, the upthrust will increase by factor 8. So first it was 10 Newton, now it will be 80 Newton. But the drag force or a viscous drag only increased by same factor. So if we increase the size, the drag force will be double. So it was 5 become 10. So what is the resultant force here? 70 Newton. What is the resultant force here? That is 5 Newton. So changing the size, increase the upthrust, so increase the resultant upward force. That is why large bubbles will reach the top of the column quickly as compared to small bubbles. Is it clear, this part? Yes, comparing, or but mass is not too effective. Like example, the weight is affecting it, but when you're comparing, these are air bubbles. So air bubbles, we can neglect their weights. Page 31, question 31B2 and C2. 31B2. The photographs, 31B2. The photographs are at a scale 1 to 12. Yeah, that is right. The drag, because the size increased, so drag force is also increasing. There is an increase in drag force because of increase in size. There is an increase in upthrust because in increase in size. But upthrust vary with the cube. So if we double the size, the upthrust will be 8 times. But if we double the size, the drag force will be only double twice, or you can mention it vary with a square. That formula in which it shows vary with a square, you're not learning that, but it also vary with a square. But the thing is that the increase in the upthrust is more than increase in the drag force or viscous drag. That's why the resultant upward force increased. So it will accelerate or greater acceleration. The photographs are to scale 1 to 12. Use a measurement from photographs. Calculate the speed of the bubble between photograph 2 and 3. The following photographs were taken at point. So the time interval is 0.33 second. So what you have, like you will compare the distance traveled by the bubble. You can take their centers. Draw a horizontal line on the center using a ruler and measure this distance. And this is 1 to 12. What is the meaning of 1 to 12 example? If it is like measurement example, if it is 1 centimeter, so actually it is 12 centimeter. The same scale, but it is 12. Means the 12 times. Actually, the scale, the figure size is 1 by 12 of original size. And the time interval, the time interval is already given in the question. They mention the photograph time interval between the photographs is 0.33. So the distance divided by time, you will get the speed. Describe an additional measurement that you would need to take from the photograph. How it could be calculated to determine the drag force. Assume that the bubbles reach the terminal velocity. So to calculate a terminal velocity, what you have to do, you have to measure the size, because to calculate, as we know it, as it is rising up, the upward force, upthrust, weight is acting down and viscous drag is acting down. So drag force and weight and upthrust, or I can say drag force is equals to upthrust minus the weight. So how to calculate the upthrust? Upthrust is equals to density, volume, and gravity. So I need for volume, what I need for volume, I need the size. Volume is 4 by 3 pi r cube. So I have to measure its diameter or the radius, and using a diameter, I can work out its volume. And using a volume, I can find the viscous, I can find the upthrust force. And weight, how to find the weight? Weight is equals to mass multiplied by gravity. And using that, we can find the viscous drag. This is one method. Another is viscous drag according to Stokes 6 pi eta rv. So we need a viscosity, we need the size, and we need a terminal velocity. Using that, we can also find the drag force. Is it clear? So first we work out a resultant force. The resultant force is actually equal to the drag force. Is it clear, this part? The resultant force is a difference. So this was assignment fluid.